Hello everyone, and welcome to the first session of this set of YouTube sessions created to demonstrate the utilization of programming and the resulting visualizations in understanding dynamics. Dynamics, as you all might know, is a branch of engineering mechanics that deals with the analysis of bodies in motion, which can be done by studying kinematics and kinetics. Kinematics is the study of the geometry of motion without reference to what is actually causing the motion, while kinetics is the study of the relation between the forces acting on the body and the corresponding motion. A particle in dynamics is a body that we consider to have a mass, but we disregard its size or shape, and we assume no rotation around its mass occurs during motion. Motion of a particle can be categorized as rectilinear motion or curvilinear motion. Rectilinear motion is motion of a particle in a straight line. The particle can move back and forth on a single axis and thus is confined in its motion to one dimension. Curvilinear motion, on the other hand, is the motion of a particle in a curved line, in a plane, or in 3D. In rectilinear motion, we use the position coordinate to define the location of the particle relative to a fixed reference that we call the origin. The motion of a particle is said to be known if the position coordinate for that particle is known at every increment of time. Therefore, we define all our motion parameters as functions of time. Let's say that we are trying to solve the problem shown on screen. The motion of a particle is defined by the relation shown, where x and t are expressed in meters and seconds respectively, and we are to determine the position, net displacement, and the total distance traveled when t is equal to 7 seconds. The manual solution involves finding the first and second derivatives with respect to time of the position function, which determines the velocity and acceleration as functions of time. Then setting the velocity equal to 0 in order to know the points where the body has changed direction while moving on a straight line. Then using these points to determine the total distance traveled by the particle. The net displacement would then be the initial position subtracted from the final position. Identical solutions can be obtained by integrating the velocity with respect to time within the interval given in question to determine the net displacement, and then integrating the absolute value of the velocity with respect to time within the interval given in question to obtain the total distance traveled. No matter which hand solution procedure you use, you will eventually realize that the solution procedure consists of a number of systematic steps that can be written into a subroutine, a function, a procedure, using any programming language in order to automate the process so that you do not have to calculate the numbers by hand after that. Today I am using the program Maple for such purpose. Maple is a beautiful computational and programming software that can make your engineering life much easier if you know how to use it. If you would like to start learning Maple, you can check the YouTube channel of Professor Scott Gold, which is very helpful in this regard. Just type Maple Prof in YouTube to get there. In the Maple document shown on screen, the user needs only to input the position x as a function of time, here, and the time interval during which the motion is to be studied. Here, in this particular example, it's 7 seconds. Maple will then derive x once to obtain the velocity as a function of time, and twice to obtain the acceleration as a function of time. Maple will also plot and animate the position velocity, and acceleration functions within the time interval given. Here I am plotting only the position function to observe more clearly the motion of the particle. This is the position coordinate x plotted versus time. Maple also plots and animates the particle as it moves back and forth in one-dimensional space. On top of all that, and using the integration procedure, Maple calculates the net displacement, the total distance traveled, and the final position of the particle. These figures generated by Maple are very important to understand the type of motion at hand. Note how the body changes directions at the instances where the velocity is equal to 0. Note what happens to the velocity when the acceleration is 0. All the interesting facts that the dynamics textbooks explain can be observed by looking at the figures generated by Maple. After solving a couple of problems by hand, it greatly helps to observe the calculated motion parameters being animated on screen. I should mention at the end of this session that the image at the beginning of the Maple document, as well as the backgrounds in the introductory material, were all generated using AI, and all the coding required to produce the Maple figures and plots of animation, as well as final results, were created by me. This concludes the first session of this set of YouTube videos dedicated to demonstrate the utilization of programming and the resulting visualizations in understanding dynamics. I will see you in the sessions to come. Best wishes.